This joint work with Tom Mrowka. I'm going to try and keep it fairly non-technical because we come from all sorts of areas into this collaboration. I'm going to be talking mostly about webs and foams. I'll begin by saying in my language what those things are. Most of the talk is about something I'm calling L-sharp. It's an SU3 Instanton homology for webs and foams, and I'll tell you what those terms mean as we go along. To me, some of the interesting things about L-sharp are the way it connects in two different ways to Tait colorings of graphs, and I'll talk about that. The construction of L-sharp involves gauge theory. I won't talk about many details of that construction, but I'll talk about enough to sort of keep it honest. The formal properties I'll spend more time on and try and explain where those come from. What's the reason for studying this L-sharp? Why did we get onto it? About 10 years ago or more, we were studying something we called J-sharp, which is very similar, but instead of SU3, it was defined using SO3. That's motivated there's a lot of the motivation for studying L-sharp. J-sharp has connections to Tait colorings as well, conjectured relationships to perhaps an idea to prove the four-color theorem in a new way. That program really relies on having a better understanding than we actually do at the moment for J-sharp, and that's really one of the reasons for studying L-sharp. I talked about the formal properties there in that outline, and then I talked about the details, which I'm not going to say much about. But in fact, an interesting thing is it turns out that the formal properties depend on the details in a to us, slightly unexpected way. The various things this connects to, I've put down some of the small selection of the things which this interacts with, and bottom there, embedded graphs in 3 space. There's actually a lot of literature on those from all sorts of viewpoints, and some of the interest for me in working on this with Tom is just seeing how what we're doing interacts with other sort of older work on spatial graphs. A slight apology that in my PowerPoint slides, that background contour from dark blue to light blue actually stops 20% of the way down, and the background is actually white in my slides. I hope it's not too difficult to read, but the black should be black on white, not black on blue here. Yeah, that's. Okay. Yes. These are webs. They're dry-variant graphs embedded in 3 space. That 3 space could be a 3-manifold. Mostly it'll just be R3. There's the unknot there. That's a vertexless loop. That's allowed. All those abstract graphs underlying those, they're all actually in that picture, I think, bipartite graphs, but that's not required. There's no orientation here. There's just edges and vertices. When we think about links in 3 manifolds, we often want to think about framed links. And I just want to briefly talk about framings for these webs. There's just a bit of binary data we want to include. So at a vertex where there are 3 edges coming in, that's these trivariant graphs, there's 2 possible cyclic orderings, clockwise or anti-clockwise, as it were, 1, 2, 3 or 1, 3, 2. So if there are n vertices, there's sort of 2 to the n different ways to cyclically order each vertex. I want to think of that choice of cyclic orderings as a sort of framing. But I only want to keep track of it sort of up to overall sign. So if I've got 2 choices of cyclic orderings, O and O primed, each one cyclically orders every vertex, I'll say they form in the same equivalence class if they agree, if they disagree just at an even number of vertices. So I'll call a binary framing a choice of one of the 2 equivalence classes of choices of cyclic orderings. There's 2 choices there. That's the theta graph drawn twice, and I've given cyclic orderings at both vertices, but at one vertex they're the same, the other vertex they're different. Those are the 2 different ways to binary frame the theta graph. So every web has 2 choices of binary framings. The blue and white backgrounds, I'm a bit sad, sorry. If you draw a planar diagram of a web, the way we would of a knot, then that sort of determines a binary framing, because it just tells you can take the rule that at every vertex you're just going to go, say, clockwise in the plane of the diagram. So there are 2 different thetas there. They're isotopic as webs in 3 space, but those planar diagrams give them 2 opposite binary framings. I won't talk much about foams, but foams, as usual, are cobordisms between webs. They are singular 2 complexes. They have trivalent seams, and they also have points where 6 facets meet, these tetrahedral points. In this talk, foams are entirely unoriented things again. L-sharp is an SU3 Instanton homology for webs and foams. What does it do? Although there's potential to define this with, say, integer coefficients, we'll always be using the field of 2 elements in this talk. And what L-sharp does, it is assigns to a web in a 3-manifold or in 3 space, a vector space, L-sharp of K, of finite dimension, which is Z mod 2 graded. It's got an even part, L0, and an odd part, L1. It's invariant of binary framed webs, but the binary framing is just there to fix the absolute Z mod 2 grading. Without the binary framing, L is just the sum of 2 pieces, but you don't know which to call even and which to call odd. The binary framing fixes that. Yeah, and that's a bit like sort of orienting a 0 manifold. There's actually a canonical choice, and you have to say, well, the other one is just minus that. Yeah. L-sharp is functorial for foams as cobordisms between webs. Since L-sharp of a web is a Z mod 2 graded thing, the map between those vector spaces might be even or odd. It might preserve the grading or flip it. To compute whether a given foam is even or odd, there's a rule here. You look at the parity of twice S dot S. You look at that and you say that's an even number, but S dot S is a half integer for a foam in 4 space, potentially. So twice S dot S is an integer, but maybe even or odd. Also, when something has boundary and you're trying to compute its self-intersection number, you need something like a framing on the boundary. And that's what the binary framing of the web does. It's just a little bit of binary data, which is enough to determine what twice S dot S is mod 2. Turns out that if the foam is embedded in 3 space, it's always even. Kind of not surprising, it's got trivial self-intersection. The understanding is then that the webs on the boundary are embedded in 2 space, they're planar, and they've got their planar binary framings. So for things in R3, cobordisms between planar diagrams, planar webs, everything is even. We can compute L-sharp for simple examples. Because L-sharp is an even and an odd part, they're like 2 Betti numbers, the dimension of L0 and the dimension of L1. And for the unknot, it's 3-dimensional and it's all in even degree. The odd part is dimension 0, even part dimension 3. Here, the theta graph, it's dimension 6 in even degree. Also 6 for the tetrahedral web there. This is the same theta graph as the other one, but it's got a different planar diagram. It's understood here that the binary framings I'm using are the ones coming from the planar diagram. So this is the same underlying web, but the opposite binary framing. And the even and the odd parts just got switched. It's 0, 6 instead of 6, 0. This one is 0-dimensional. There's no L-sharp vanishes. More examples. That's an embedding of the Peterson graph at the top left there. For that particular spatial embedding of the Peterson graph, the homology has rank 4. Top right is the dodecahedron, one skeleton, it's dimension 60. This one in the bottom left is an embedding of the complete graph, complete bipartite graph on 6 vertices, K33. With that embedding, the Betti numbers are 6 and 6. Bottom right is the trefoil knot, and the Betti numbers are 5 and 2. So these are the Z-mod 2 Betti numbers of L-sharp. That last one is particularly significant because it contradicts something which Tom and I believe, largely because of my mistake, something we believed for about 30 years, which was that we believed that when we finally wrote down a paper with the details of L-sharp, it would be clear that L-sharp did not change if you changed an overcrossing to an undercrossing or vice versa. For a year or more, we realized that this couldn't be true. And it wasn't until about a couple of months ago, I'm not quite sure, quite recently, Tom finally found where the mistake was. It had been sitting there for a long time. Anyway, 5-2 is the trefoil. That left-hand guy there is the Peterson graph again. If you tie a knot, trefoil knot in this case, in one of the edges, it makes a difference. It's now 6. But it matters where you tie the knot. There's no symmetry between those two last guys because of the way the overcrossings work. They're kind of different. I'll try and explain that later. Because there are 2 Betti numbers, even and odd, we can take the difference, and that's the Euler characteristic of L-sharp, L0 minus L1. And from the examples we've already seen, for the Peterson graph with that embedding, it's 0, 60 for the dodecahedron, 0 for this embedding of K33, and 3 for this trefoil knot. So this is an invariant of binary framed webs, this number, and we can ask what it is. It's just some integer. So there's different ways to say what that number is without talking about instantons. Because I like Tait colorings, I'm going to say it in terms of Tait colorings. So Tait coloring is a edge 3 coloring of of the web. Every edge is colored with one of three colors, and you should have three different colors at every vertex. When my web is framed, when I give you a cyclic order at each vertex, a priori, then you can compare the cyclic ordering I gave you, the framing, I can compare that to the cyclic order in which the colors come at that vertex. In this theta web here, assuming that I'm giving it the binary, the planar binary framing, so the natural thing is anti-clockwise at each of the vertices. And if I order the colors red, blue, green, then on the left I've got +1 because it's anti-clockwise red, blue, green. On the other side it's clockwise red, blue, green, so that's a -1. So given a Tait coloring at a vertex, there's a sign for a binary framed web. And if I take the product over all the vertices, I've got something which is a sign attached to the Tait coloring itself, tau. There's a -1 to the half number of vertices over 2 there. That's there because I want the sign of that Tait coloring to come out to be 1, which it does. So in a package there, given a binary framed web and a Tait coloring of it, that Tait coloring falls into one of two classes, positive or negative. So I can either count the Tait colorings, add up one for each Tait coloring, or I can count them with sign, sum of +1s and -1s. The conventions are laid out. It's not hard to check, but if K actually lies in the plane, whoops, what happened? I don't know what happened. There we are. If it actually lies in the plane, then they all come with sign +1. So the number of Tait colorings is the same as the signed count of Tait colorings, but in general, that's not true. So it's just some integer invariant of framed webs. I wondered how many different places in the literature this was already known. It turns out that this quantity is also the value of the Yamada polynomial at 1. An integer invariant, you need to restrict that to trivalent graphs. Greg Kuperberg pointed out to me that I ought to really write it like this. You put the sort of alternating thing at every vertex and the inner product on every edge. Each index, like I, runs through 1, 2, 3, and the spots in which they live are the sort of ends of the edges. The Einstein summation convention is sort of implied there, sort of Penrose-style connections there. This is planar, so all the Tait colorings come with sign 1. There are 6 Tait colorings. This is interesting. This is the complete graph K33. It has 12 Tait colorings, but they fall into 2 different types. Half of them are even and half of them are odd, and representative ones are there. So the signed Tait count is 0. And if you like, that's a proof that this bipartite graph is not planar. Or you can do the usual thing of drawing 3 houses and 3 whatevers and try and connect them up. So going back, I was asking what is the Euler number of L sharp of K, and this is the answer. It's the signed count of Tait colorings. So that's the first connection between L sharp and Tait colorings. There's another connection here. I was just looking at the clock to see if I've used 40 minutes or I've got 40 minutes left. I think it's the latter. This is another theorem connecting L-sharp to Tait colorings. If K lies in the plane, then it turns out that the odd Betti number is 0. Along with that, that means that the dimension of L-sharp OK is the same as the Euler number, which is the signed Tait count. But then the first theorem says that but the previous slide had a lemma that the signed Tait count is the same as the Tait count. So these two things are special to planar webs. That doesn't mean that the graph is an abstractly isomorphic. Oops, I keep accidentally pressing the buttons. Doesn't mean that, I'm not saying that it's true when the graph is abstractly planar. I'm saying it's true when the web, as a spatial web, actually sits inside a plane in 3 space. Theorem 2 is not proved in this order. I mean, theorem 2 is just proved, as I'll explain, by just analyzing planar things directly. And the vanishing of the odd Betti number is sort of a corollary. The formal mechanisms of these, I mean, perhaps in the spirit of categorification, and when I said L-sharp in some states categorifies the signed Tait count, but also in the sense that there's a Skein relation for the signed Tait count, which becomes an exact triangle for L-sharp. So L-sharp has these Skein exact triangles. As usual, these diagrams represent little pieces of a diagram of a web. So in the first row there, you have 3 webs, which in some planar projection look like that inside this region and are the same outside. Those arrows imply that there's a long exact sequence, periodic of period 3, or an exact triangle of linear maps induced by actually elementary cobordisms between these. If you ignore the little crossbars, that's just what's left looks like the standard unoriented Skein sequence, but there were just 3 bars, as it were, one in each thing added to those. L-sharp also satisfies, in the second row, a very similar exact triangle, but instead of adding a bar to all 3, a bar is added to just one of one of these guys that's there. It turns out that you can put that bar on any of them, so there's also this third exact triangle illustrative here with the bar there. These are planar diagrams, planar projections of webs, so they come with their planar binary framings, anti-clockwise at every vertex. And then you can ask whether these maps are even or odd. The red ones are the odd maps, the green ones are the even maps. That last one, if you rotate all these guys, then those 2 last, rotate. I don't know if I already did it. So that guy is now the same as this guy, and this guy is the same as that guy. These 2 creatures are almost the same, but one's an undercrossing and one's an overcrossing. From the long exact sequences, you can compute the, you've got to get the signs right, but this tells you that the Euler number for this guy is just the difference of that one and this one, and same down here with the same signs. So these exact sequences just tell you that those 2 things up there, they've got the same Euler number, those 2. So the Euler number is just an invariant of the binary framed web, not with its spatial embedding, but just sort of abstractly. And that's encapsulated in that lemma there, which we just sort of deduced from these exact sequences. These exact sequences, they fall into this octahedral diagram. Every edge there is a map from an elementary cobordism. Some of them have even degree, some have odd degree. Those red triangles, which is 4 of the 8 faces, are the Skein exact triangles that we've seen. The remaining 4, which are either even, 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 or odd, odd, even, are commutative triangles. They all express the fact that one map is the composite of the 2 others according to the directions of the arrows. If you do a sort of diagram chase of Euler numbers, rather as I just did on the previous slide, the alternating sum of the Euler numbers of the 4 highlighted guys there, which are the 4 planar ones, alternating sum of the Euler numbers there is 0. That's something that also holds for Tait colorings. It's the Tait relation for the number of Tait colorings of a graph. So that Tait relation is one way to prove the result stated earlier, that for planar graphs, the Euler number just comes out to be the number of Tait colorings. I'm going to return to that, but with a different argument. Returning to the Euler characteristic of L-sharp, we've established these properties of it, and they're now quite enough to entirely determine L-sharp. You can compute the Euler number of L-sharp from the properties we've seen. Euler number is 3 for the unknot. I think I stated that. Crossing changes don't change the Euler number. The sign of the Euler number depends on the binary framing. I didn't state this, but it's sort of fairly straightforward to prove from the gauge theory. It's multiplicative for disjoint unions. Importantly, the Euler number has this Skein triangle, this Skein relation. All these properties entirely characterize the Euler number of L-sharp. They're all satisfied also by this signed Tait count of colorings. So that's just the proof that the Euler number is equal to the signed Tait count of for the web. Just reduce it to this, basically this Skein relation is the key thing. So how is L-sharp actually constructed? When we have a web in a 3-manifold, trivariant graph in a 3-manifold gives the data for an orbifold structure on the underlying 3-dimensional topological space. You want to think of putting a geometry on Y where along those edges labeled 2 has a structure of an orbifold with a Z mod 2 stabilizer, which means there's a cone angle in the geometry, cone angle of pi instead of 2 pi, all the way along that edge. There's some Klein-4 group thing going along at the vertices. For now, all the edges are labeled by the number 2, meaning the stabilizer is order 2. Such a thing that's an orbifold has an orbifold fundamental group. For typesetting purposes, I'm calling it O pi for orbifold pi 1. That's the ordinary fundamental group of the complement of K. Modulo relations, and the relations say that there's order 2 for those little loops going around the edges. This one has infinite fundamental group. It's covered by some torus bundle over S1. I put that on a slide because there's a paper by Dunbar which sort of classifies all the all such orbifolds whose geometry is not hyperbolic, essentially irreducible examples anyway. Given a group, we can look at its representations or its homomorphisms to some other target group. We're talking about SU3 homology here. So what I'm interested in is homomorphisms from the orbifold fundamental group to SU3. Because meridians are elements of order 2 in the orbifold fundamental group, they have to map in SU3 to elements of order 2 or possibly 1. But I don't want them to map to elements of order 1. I want them to map to elements of order 2. I want to consider the set of all such homomorphisms, and that's, I'm calling that R-sharp this. I'm calling that the framed representation variety. There's also the unframed representation variety, which is where I just do the natural thing of just considering these things up to conjugation by elements of SU3. The unframed representation variety is the natural thing from many points of view. It sort of classifies, it just describes flat connections up to isomorphism. But there's a way to turn the unframed thing into a framed thing, which is a device we've used elsewhere. If you take your orbifold determined by y and k and just connect some other little gadget to it, some other orbifold, something we call an atom, so chosen that its representation variety consists of a single point, and a single point with, which is an irreducible representation. If you add that atom to yk and you take the unframed representation variety, that's the same as the framed representation variety of the original guy yk for sort of straightforward fundamental group reasons. So that's behind the scenes a device we'll be using to make the gauge theory sensible. And we really want to use the left-hand thing, even though the right-hand thing is the thing that's easier to describe. There are other choices of atom. This will sort of come later in the talk if I don't run out of time. The tangled handcuffs there are an alternative atom. The green atom up there is different from all the other sorts of orbifolds we're using, because instead of having order 2, it's got order 3 stabilizer along those sort of hop flink things. I won't sort of talk further about the details, but that's there's 2 essentially different choices there. What does the framed representation variety look like? Oops. For the unknot, it's CP2. For the theta graph, it turns out to be the flag manifold. These things are all very easy to verify. That's the flag manifold for complete flags in 3 space, SU3 divided by the maximal torus, a 6-dimensional real manifold. For those tangled handcuffs, the representation variety, there's a single irreducible representation variety, so the framed representation variety is SU3 divided by the center, it's PSU3. So those are some examples. Here's a more interesting example. This is Kinoshita's theta curve. It's an embedding of the theta graph in 3 space. This particular image is snapped from a paper in a life science journal studying proteins. The title of the paper is Theta Curves in Proteins. And it has pictures which, to someone interested in proteins, are much cooler than that one. But for someone interested in theta graphs and topology, that one will do. Kinoshita's knotted theta curve appears a lot in the literature. Different image credit there. That's a much better picture of the Kinoshita theta graph, which shows it's got this sort of 3-fold symmetry. If you go back to the previous picture, whoops, it's got a Tait coloring there. Tait colorings determine a representation of the orbifold fundamental group in the Klein 4 group, V4. Red, blue, green mapped to the three, their meridians mapped to the three non-trivial elements in the Klein 4 group. So it doesn't really depend on the knotting there. There's a abelian representation of the fundamental group in the Klein 4 group. But actually, the fundamental group for this orbifold is something much more interesting. It's an extension of V4 by the binary icosahedral group. I learned that the other day, and I was kind of surprised because I can't see an icosahedron right there. But that's what it is. It's extension of V4 by the binary icosahedral group. Furthermore, although the binary icosahedral group is the kernel, there's also a map from OPI1 to A5, the icosahedral symmetry group. A5 itself maps into SU3 in two different ways, differing by the outer automorphism of A5. So there are two more conjugacy classes of homomorphisms. If I look at all the homomorphisms together, that's the representation variety I'm interested in. The abelian representations into the Klein 4 group, one conjugacy class, but they form this flag manifold. The two irreducible ones, two different conjugacy classes there, they form two copies of PSU3 in the framed representation variety. So that's three components there. Once you've got this framed representation variety, there's a lot of literature already on telling you what to do now to construct an Instanton homology group. And what you do is you interpret these framed representation varieties as the spaces of flat connections, flat bundles, on the orbifold, or the orbifold plus an atom, because you want that R sharp rather than just R. You interpret the flat connections as the critical points of the Chern-Simons functional, a function on the space of all connections, flat or not. You perturb the Chern-Simons functional so that it has more Smale properties. And once you have this more Smale property from perturbations, and once you understand how Uhlenbeck compactness plays into your story, it's a standard procedure really to define L sharp for this orbifold as the Morse homology of this Chern-Simons functional. So it's generated as the critical points, and the boundary map counts trajectories of the Chern-Simons flow. Roughly speaking, you should think of L sharp, if you want to, as it's like the homology of the framed representation variety, but with extra differentials coming from instantons, which are non-trivial trajectories of the Chern-Simons flow. The mod 2 gradings coming from the binary framing of the web are a little bit subtle to see from that point of view. Warning. Here are some examples. For CP2, it turns out the dimension of L sharp is 3. Saw that on a previous slide. 3 happens to be the Betti number of CP2. With Z mod 2 coefficients, L sharp is just the homology of the representation variety for the unknot there. For the theta graph, very similar story. The representation variety is the flag manifold. The dimension of L sharp coincides with the dimension of the homology of the flag manifold, which is 6. For the tangled handcuffs, however, there's a non-trivial representation variety, PSU3, with Z mod 2 coefficients. Its homology has rank 4, but L sharp does not have rank 4. It has dimension 0. Theorem 2 said that for planar webs, the dimension of L sharp just counts Tait colorings. I want to explain how that works. Most of what I'm going to say in the next few slides doesn't really depend on planarity at all. So there's sort of standard TQFT stuff happening to start with. If you look at the unknot, there's a cobordism from 2 copies of the unknot to 1, this pair of pants. That makes, in a L-sharp of the unknot, an algebra. It's an algebra with 1. The identity element 1 is the element of L-sharp of the unknot provided by that disk whose boundary is the unknot. What is this algebra as an algebra? You can describe it as follows. It has a distinguished element x, and it's just the quotient of the polynomial algebra in x by that cubic relation, x cubed plus x is 0. Different ways to say what x is. The real way to talk about it is to talk about a line bundle on the space of connections associated to a point on the phone. After the fact, you can define x in the in L-sharp of the unknot as the element provided by this rather particular foam here, which is a genus 1 surface with an extra disk added to it. That relation x cubed plus x equals 0 is a reflection of something which was, in a very different context, computed by Yi-Xie. In principle, this is dependent on our choice of atom. And that's kind of a more important point than we realized when we started this project. There's an algebra, which is the homology of the unknot, and then for every other web, we've got a module over that algebra. If I pick an edge E of a web, there's a standard picture here of a cobordism from the disjoint union of the web and the unknot to the web. So that gives a map from A tends to L sharp of K to L sharp of K, and that's the module structure. Again, a sort of standard picture for these sort of contexts. We have one such operation for each edge. And these operators commute. Just for one operator, because x times x squared plus 1 is 0, there's a direct sum decomposition of the kernel of x and the kernel of x squared. I don't know why I wrote x squared minus 1. It's mod 2, x squared plus 1. Direct sum of the 2 kernels there. There's one such decomposition for every edge, but they all sort of commute, so they're all consistent. That's hard to read, but I give you some subset of the edges, call it S. For every edge in that subset, I look at the kernel. For every edge not in that subset, I look at the kernel of x squared plus 1. Take all the intersections. So if there are like k edges, then there's 2 to the k subsets, and there are potentially 2 to the k different summands in that summand decomposition of L sharp of k. It turns out that there are relations between these operators when edges meet at a vertex. And those relations imply that that summand is empty. It's the 0 summand, unless that one set S, unless that set S is called a one set or a perfect matching, just a collection of edges such that every vertex is seen once. So rather than all subsets of E, it's a sum over one set of edges. And instead of that big intersection thing, which is hard to read, I'll just abbreviate that as V. So given a web, there's this homology group. It's a direct sum of summands V, one for each one set. There is the unknot. It's got rank 3. The one set is allowed to be the one edge itself. That's the gray guy. Or the one set, in this case, could be the empty set. It's a bit hard to figure out what a one set means if there aren't any vertices, but that's what it means. Definition of a one set is that for all vertices, ... And so anything's a one set. The kernel of x then is one-dimensional. The kernel of x squared plus 1 is two-dimensional. That's just what the algebra looks like already. of course. But this one-set decomposition just makes it very easy to understand planar graphs. Here's the cube. We believe its L-sharp has rank 24, which is also the number of Tait colorings. Well, why is it 24? Well, L-sharp of the cube has got this decomposition according to one set. Each of those 9 diagrams there, the one set is the little gray edges. What's left in bold red is a 2 set, and it's a collection of simple closed curves. Importantly, this is a diagram in the plane. So the simple closed curves are simple closed curves in the plane, and they're not, therefore, knotted or linked or anything. The other thing that's important for the calculation is that the one set doesn't really matter. If I look at one of those 9 diagrams and want to know what's the dimension of the corresponding summand V, I don't need to know the details of the one set. All I need to know is whether the one set has an even number of ends or an odd number of ends on each of the components of the red set. It's a sort of parity thing. Everything is even there. I could actually delete all those gray edges and nothing would change because I wouldn't have changed the parity. So really I'm just computing something for, well, for the first 6, it's just a single unknotted loop. And for the remaining ones, it's 2 unknotted loops. For an unknotted red loop, top of the slide, dimension is 2. So 6 copies of 2. For 2 unknotted loops, which is the remaining 3, it's 2 squared. 6 times 2, 3 times 2 squared is 24. This is just a simple way to compute, the combinatorial way to compute anything in the plane. And if you think about it not very long, you'll realize that it's also a simple way to compute the number of Tait colorings. It's the same. You'd be doing the same calculation if you wanted to compute the Tait colorings that way. So this is a proof of theorem 2, essentially, illustrated in this case. Simple calculation for dimension of L-sharp, simple calculation for Tait colorings, and they're the same thing. So it's important that this was planar. This is non-planar. I've tried to draw the one sets and then in bold red the 2 sets. There's 6 of them. I've drawn the first 2. My drawing isn't very good, but even if it were better, I don't know how much it would help. The red set on the left there is a hop link, and on the right, it's an unlink. They're not joined by an even number of gray edges. They're joined by an odd number of gray edges. It's different from the previous case. So simplifying those pictures as much as possible, the first one is a hop link with a single odd number of edges, this gray edge there. The next one is an unlink. The unlink gives you 0. The hop link gives you 4. If you draw all the 6 one sets, it's only one of them, which is that hop link. The rest are all unlinks, as it happens, for this spatial embedding. So the dimension is 4. So the non-trivial calculation there is for that hop link with an extra bar. I haven't told you how to do that calculation, but it can be done with exact triangles. Yeah. It depends on the choice of atom, and I will say that again in a couple of slides' time, I think, yes. In general, if you wanted to compute for non-planar graphs, you'd have to be able to compute red loci which were knotted. We call this the red homology, for example, of a knot K. One of the things you'd have to compute. We haven't written this down. I perhaps call this work in progress, but there's a spectral sequence from the ordinary Khovanov homology with mod 2 coefficients to the red homology of K. Happens to be a spectral sequence in which nothing happens after the E2 page, at least for the trefoil. the very beginning, I talked about J sharp of K, which is the same thing almost, but it's defined using SO3 instead of SU3. It long predates the work we're doing now. J sharp had a beautiful property proved using sutured manifold decompositions, which is that it's non-trivial, non-zero for, at least for bridgeless webs. It was conjectured to count the Tait colorings. That conjecture is still open when K is a planar graph. The point being that if you take these things together, it implies the four-color theorem, because four-color theorem is equivalent to saying that bridgeless planar trivalent graphs admit a non-zero number of Tait colorings. How do these compare, the SU3 and the SO3 stories? In some features, they look exactly the same. They satisfy the same exact triangles. In writing down the proof of the exact triangles for SU3 involves some moduli spaces of small dimensions on very simple foams. It was kind of surprising how identical the proofs looked. And if you know any sort of, when you actually do the gauge theory, the formula for the dimension of a moduli space for an SU3 moduli space on a foam looks very different from the SU2 or the SO3 case, but somehow these particular foams, they just work out to be exactly the same. J sharp does not have a mod 2 grading. It's not graded by Z mod 2Z, it's graded by Z mod 1Z. And there's no Euler number, therefore, for J sharp of K. So those results have no counterpart. The important difference really is that x cubed is 0 is the cubic relation that is satisfied for the unknot with J sharp. So that's the simplification. It's like a sort of Lie-type deformation. Going from x cubed equals 0 to x cubed plus x equals 0 makes everything much simpler. That's why this one set, two set stuff came in. We don't have that for J sharp of K, so we can't compute it for planar graphs. We don't know what is the dimension of L sharp for that dodecahedral web. That's the sort of first case that's really interesting, and we just don't know the answer. We do know it for L sharp on account of the simpler potential there. L sharp does not have a non-vanishing theorem for bridgeless webs. J sharp has to be non-zero for that guy. It's a bridgeless web theorem, non-zero. L sharp is 0. I think J sharp has rank 4 for this thing. L sharp is 0. Very briefly, and to close, we could use the tangled handcuffs instead of that green atom. Haven't got much to say about this, but I'll call it LTHC for tangled handcuffs. Different atom, same exact triangles, same mod 2 grading, same Euler number. But now, with that atom, x cubed plus x is not the relation, it's x cubed. X cubed equals 0, just like J sharp. So this, again, we can't compute. There's no direct sum decomposition according to one sets and two sets. Can't compute it for planar graphs. Might have a non-vanishing theorem for bridgeless webs. A plausibility argument, which is probably not turnable, interval, a proofable thing, is to try and compare it to SO3 using a Smith inequality type thing for Z mod 2 actions. Thinking about what this really involves, if you want to show that dimension of L sharp really counts Tait colorings, a different way to say it is to say, well, it's Z mod 2 graded. You're trying to show the odd Betty number is 0, because you know what the Euler number is. So think about it that way. Try and prove that for a planar graph, the odd Betty number is 0. And as I said, there might be at least a speculative plausibility argument for non-vanishing in terms of a Tait Smith inequality for a Z mod 2 action on the configuration space, something which works for the tangled handcuffs, but not for the green atom. So that's all I have to say. I've left myself 5 minutes and 5 seconds for questions, and thank you very much for listening.